Hello, my name is Kanami Fukuoka, and I'm a junior student majoring in computer science at Keio University in Japan. This summer, I've been working at the Oton Lab under the supervision of Dr. Otto Topolsky with close mentorship from Dr. Ji and Tae. Today, I will present my project on multivariate regression for physiological features from time series foundation model embeddings. This project asks two questions. First, what physiological information is accessible from a frozen foundation model representation? Second, does predicting related physiological features jointly provide an additional benefit? Time series foundation models are now applied to many downstream tasks, including forecasting, classification, anomaly detection, and imputation. However, most studies focus on final task performance. We still know much less about what information is actually retained inside their representations. Strong downstream performance does not necessarily mean that the embeddings preserve clinically meaningful information. And physiological signals provide a useful setting for studying this question because a single ECG waveform contains several types of information, including rhythm, beat-to-beat variability, waveform morphology, and amplitude. Therefore, rather than evaluating only downstream performance, this project investigates what physiological information remains accessible from frozen time series foundation model embeddings. This project builds on preliminary work that used frozen moment, which is a time series foundation models developed in the Oton lab, and they used its embeddings to predict physiological features and found that the embedding-based representation often outperformed raw signal inputs, especially for periodicity-related features. However, each feature was predicted independently, so this was an N-to-1 formulation, with one separate regressor for each physiological target. My project extends this setting to N-to-M prediction, where one model jointly predicts a vector of physiological features. This is motivated by the fact that several targets are derived from the same underlying physiological events. For example, heart rate and hour interval are both determined by hour peak timing. Their relationship is approximately inverse, so when hour interval is measured in seconds, heart rate is approximately 60 divided by hour intervals. So the main new question is whether sharing information across these outputs provides an additional benefit beyond representation quality alone. This is the overall pipeline for this project. First, each physiological signal recording is divided into fixed length windows. Each window is passed through a pre-trained moment encoder. The encoder remains frozen, so only the downstream regression models are trained. Moment applies reversible instance normalization or rev-in to each window. This normalization removes the original window level offset and scale from the encoder input. To restore this information, I append the mean and standard deviation of the original window to the frozen embedding, and I refer to this combined input as the concatenated embeddings. I then evaluate two prediction strategies. Independent ridge regression trains one model for each target. Multivariate partial least squares, or PLS, learns shared latent input components and uses them to predict all targets jointly. I evaluated a method on both synthetic and real-world electrocardiogram, or ECG, data. The synthetic dataset contains 5,000 ECG windows generated using NeuroKit-2. Heart rates were uniformly sampled between 30 and 150 beats per minute. The real-world dataset is the MIT BIH arrhythmia database, segmented into 70,328 windows. Both datasets were sampled at 360 Hz and divided into fixed 5-second windows. For downstream regression, the data were divided into training, validation, and test sets using an 8:1:1 ratio. I evaluated 14 physiological targets. Periodicity-related targets describe rhythm and heart rate reliability. Morphology-related targets describe the timing and shape of the P, Q, R, S, and T waveform. The amplitude-related target measures the voltage difference between the R and S peaks. To evaluate a representation, I use relative RMSE. The RMSE from the concatenated embedding divided by the RMSE from the raw signal using the same regression model. A value below 1 means that the concatenated embeddings has lower error. Before examining regression performance, I visualize the moment embeddings using PCA and TSNE, with each point colored by heart rate. The synthetic embeddings show a clear and smooth heart rate organization, In particular, the TSNE projection forms a curved structure with a consistent color progression. In contrast, the MIT-BIH embeddings are more overlapping and locally fragmented with substantially mixed heart rate colors. However, these are only two-dimensional projections. Predictive information may remain accessible in the full embedding even when it is not clearly visible in PCA or TSNE. The first result concerns representation quality. Thus, the concatenated moment embeddings outperform the raw signals within the same model. On synthetic ECG, the results were selective. With rich regression, the concatenated embedding had lower RMSE for 6 of the 14 targets. With PLS, it had lower RMSE for 4 targets, and these gains were concentrated mainly in periodicity-related features. The MIT-BIH results were much more consistent. For all 14 targets, the concatenated embedding had lower RMSE than the raw signal under both rich and PLS. For example, under rich regression, the relative RMSE was 0.458 for heart rate, 0.454 for RR interval, and 0.305 for RS amplitude difference. These results suggest that the representation advantage is particularly clear under the variability present in real-world ECG. The second result concerned joint prediction. Here, I compare multivariate PLS with independent rich when both models use the same concatenated embeddings. On synthetic ECG, PLS had lower RMSE in the current test split for 3 of the 14 targets, SDNN, RMSSD, and PNN20, and these are all HRV, heart rate variability related features. On MIT-BIH, PLS had lower RMSE for 4 targets, PL interval, QT interval, SD segment slope, and T-wave gradient. These are mainly morphology-related features. However, these improvements were generally modest, and rich had lower RMSE for most of the remaining targets. Therefore, the evaluated joint model did not provide a consistent overall advantage. Instead, the results suggest that the benefit of output sharing may depend on the physiological target group. There are several possible explanations for this target-dependent result. First, periodicity, morphology, and amplitude features may depend on different parts of the signal and different predictive directions in the embeddings. Forcing all targets into one shared low-dimensional space may therefore discard target-specific information. Second, statistical correlation does not necessarily imply a relationship that is easy for linear shared model to exploit. For example, heart rate and RR interval have a nonlinear inverse relationship. Third, the target differ in scale, noise, and predictability, which may cause negative transfer. There are also important experimental limitations. Rich and PLS are different regression methods, so the current comparison doesn't isolate the effect of output sharing alone. In addition, the ECG windows were randomly split. This means that windows from the same recording may appear in both the training and test sets, which could make performance appear better than it would be on completely unseen recordings. Future work will therefore use recording level splits to avoid this overlap. I will also compare PLS1 and PLS2 under the same conditions. PLS1 fits one target at a time, while PLS2 predicts several targets jointly using shared components. This comparison will more directly isolate the effect of output sharing. Additional future work includes reduced rank regression, grouping physiologically coherent targets, repeated evaluations, and measuring whether the predicted features preserve physiological relationships, not only whether each individual RMSE is low. In conclusion, the concatenated moment embedding showed a strong and consistent advantage on MIT-BIH, lowering RMSE for all 14 targets within both regression models. The synthetic results were more selective. Joint PLS produced lower errors for a small number of HRV and morphology targets, but it didn't provide a general improvement over independent rich regression. The main takeaway is that representation quality and output sharing are different questions. A useful representation doesn't guarantee that jointly predicting correlated targets will improve every feature. Future experiments should therefore focus on sharing within physiologically coherent target groups and evaluate both individual feature accuracy and preservation of physiological relationships. Thank you very much for listening, and I would especially like to thank Rachel Burson and Dr. John Dolan for organizing the RISC program and creating such a valuable research environment. I am also sincerely grateful to Dr. Otto Tobolsky, Dr. Chiante, and the members of the Autumn Lab for their guidance, insightful discussions, and continuous support throughout this project. I gratefully acknowledge the support that enabled my participation in the RISC program as part of the support of SoftBank Group Corp and ARM. Thank you.